Excellent. So how many of you know a lot about neural networks or a medium amount of knowledge? Okay. Okay, that's good. I have a fairly building up on like a little bit of neural networks background, trying to put things in perspective with the new renaissance of what now it's called deep learning. I am a research scientist at Google. I actually moved last week from Google Brain, which is down the road, to DeepMind, which is in London. So last week I was in London, and so I'm doubly jet lagged, but hopefully still all here. And yeah, so a little bit about myself and how I got into deep learning. I have a background in mathematics and telecommunication engineering from Spain. I'm from Barcelona, and I did a master's at UCSD, my PhD at Berkeley. But it really was actually during my internships at Microsoft Research where I got to meet a lot of the students by Jeff Hinton, who is a professor from Toronto who is a pioneer in neural networks. And as a result, my thesis topic was actually like in deep learning, namely optimization and recurrent neural networks. And once I finished from Berkeley, I joined Google Brain, and now very recently I moved to DeepMind, which are, and these two groups definitely have neural networks are kind of their driving force in several ways, I hope to communicate today. First and foremost, though, I would say that a lot of what I'm going to talk about is done with great collaborators, most of them at Google or have been at Google Brain. It's been a great 2 years for me to learn and grow, and of course it was nice out of the PhD to sort of join a group where deep learning was the driving force. You might know a bit about history about Google Brain, but actually it was Andrew Ng, who is a professor here, I believe still, was part of the initiator at Google back in the day. So I have to say that a lot of the work, I'm presenting here, it's done in collaboration, and it's, of course, extremely important to acknowledge those guys and many others that are not here. And so I hope to convey maybe a little bit of deep learning and my own take on deep learning, so I'm going to give a little bit of an overview. Please, if you have questions, if you're curious about anything, you can ask anything throughout the talk. Let's keep it informal and so on. Then I'm going to dive into more of a technical aspects that is something that I've done a lot of research on the last couple of years. And this is definitely sort of a new paradigm that's sort of starting to explode again after some recent advances in computer vision, namely recurrent neural networks to deal with sequences. So it's quite interesting. And then if we have time, I'm going to describe some of the new paradigms which deal with memories and attention mechanisms that you can add to these neural networks that allow them to be more and more closer to computers. So you probably have seen some version of this slide where it's basically saying, yeah, deep learning and machine learning, in fact, are very hot topics nowadays. There's a lot of money from big companies, from startups, lots of investing, lots of from finance to medicine. It's sort of taking, especially machine learning rather than deep learning, is really like being used everywhere. I would say it's hard to not find applications of machine learning or places where it could be applied. And this is just simply showing sort of Google trends. Where you kind of see some sort of maybe exponential growth on machine learning queries and quite correlated with deep learning. And then the previous hot thing was super vector machine. It sort of was discarded by this naive graph in 2012, which makes sense, that was the big ImageNet year for convolutional neural networks. So on that note, simply, I like to see deep learning not as something like magical that solves AI and so on. I really have a very pragmatic view on what deep learning is, or rather supervised learning. And what it is, it's basically a mapping from an input to an output. And here the input would be an image, so a set of pixels, which you could think as a vector or a matrix. And given this image, you want to classify whether there's a cat or a dog. and you're given many pairs of examples through supervision, so through some human labelers. And with that, you essentially train this convolutional neural network or neural network to fit a function. So more precisely, we are trying to find a mapping that goes from X to Y as best as possible for a given training set of X and Y pairs. And we do so by simply optimization, and here is where like distributed optimization and systems come into role, especially where something that typically has been done at Google Brain. So you define this mapping f of x, which can be a neural network, or it could be also, of course, a linear classifier or whatever you want. And you define a loss over this function, over the whole training set, and then you're set to find parameters of this function f that minimizes this loss. And this is almost all you need to know. So perhaps this is why entering or understanding machine learning is sort of easy, because this is really almost all it is, except there's lots of tricks, of course, and making things work is sometimes not as easy as just applying these mindlessly. And I think deep learning has really been successful as sort of fulfilled this promise of, I don't want to know too much about the underlying x's and y's, but I have sort of a generic algorithm that allows me to map all sorts of modalities and interesting signals input to output. And deep learning indeed has done quite well. So it is part of, or currently mostly in a state of the art on several tasks, some of which I've been sort of involved or more involved through, because they're involving sequences such as language modeling, machine translation, or image captioning. But there's really a very wide variety of applications where neural networks seem to help push the state of the art. And that's why probably it's such a hot topic to work on. But I think for the most part, even though I have a speech recognition background, and the speech deep learning revolution started actually quite early in 2008, perhaps, this was a result that made the computer vision community really believe in these convolutional neural networks, which is a particular kind of neural networks. And this was done largely thanks to a data set which was collected by Fei-Fei Li and others here at Stanford, which just basically had a bunch of images with labels of objects that were present in the image. So here is an example. And by having a lot of images, namely for the classification task, 1 million images, 1,000 classes and 1,000 images for each class, you would want to train this f of x that maps from x, the image, to one of these 1,000 classes. And one of the architectures that did fairly well last year and also this year with some modifications is what people call this inception architecture, which is essentially many layers of computation. I haven't quite described what these layers are exactly, but bear with me on that. This is just showing the input there on the left, very small, that's the x, and then there's a bunch of layers that are all differentiable, so we can all compute the gradients efficiently. And at the end, we just predict one of these 1,000 classes. And now the winning architecture this year, I believe, is this is 20-something layers, and the winning is 150. So really, it's getting a little out of control, especially in vision, I would say. But apparently add some layers, tune a little bit the architecture, you get better and better at classifying these objects. In fact, it's getting at a level where perhaps an untrained or a human that might get tired to classify objects across 1,000 might do even worse than the current state of the art. And this must be updated because the new result actually halves the error rate of the previous best result, which was last year archive paper. So that's not. So the 2014 was the official result, and the 2015 is as I said, halving that archive 2015, or almost halving the error rate. So the progress and the pace of papers out and so on is quite almost unbearable. But there's really like a lot of exciting ideas and many people definitely working on this field. So it's fairly exciting. And then the bottom line is you can do fairly difficult things like, I don't even know what these flowers are. I mean, I know they're flowers. But these neural networks give you some sort of classification that's fairly fine-grained. And they kind of, statistically speaking, do a reasonable job whenever there's some doubt. I mean, there's lots of objects in this image, so what should the network do? In general, whatever it outputs is fairly accurate. And then whenever it makes mistakes, they happen to be within reason. I mean, that's not a snake, but it certainly looks like one. And I mean, that's not a dog, but it looks like a dog at least. And so the net result of all these, which is why perhaps large companies such as Facebook or Google are interested, is that now you're able to do large amounts of computation automatically on large amounts of data at very cheaply, in sense, basically just using a bunch of computational resources. So in Google Photos, for example, you can do cool things like look for pictures you've taken on the sea or even videos without you needing to go over every picture that you take and labeling them. So that's a feature that got launched, and the key technology behind this is obviously these neural nets or convolutional neural nets that I was describing. And then you can even do some other funkier classes like drawing or Yoda, and it fairly, I mean, that's kind of a strange Yoda, but actually I believe that's a real example from someone in our group. So I keep it there. I hope it's a real one and not, Then you might have seen also like all sorts of things. So I think the amount of people in the field makes really like surprising, you get surprising side effects because you have this social network effect where like people start trying all sorts of crazy things. So this is sort of an interesting experiment which was done by several groups, but Alexander is actually also at Google, not at Google Brain, but he's in the computer vision team. And you might have seen this, but essentially you can take any picture and sort of let the network imagine, or rather you optimize, instead of just passing the image through the network, you say, I want to have certain class at the output. I'm going to optimize with respect to the input. So you sort of reverse the optimization problem. Instead of finding the best parameters, you find the best x for a given y, and you initialize that x with an image, and then you get all sorts of cool images that look like art. And further, some guys from Europe took this further and did this sort of merging a base image, which is a picture you can take like that river, with all sorts of artistic styles. And here, sort of the way to do this is also through a neural network that was trained on ImageNet. And you just take the base image and you say, I want the high-level features of this network to map to the real image, but the low-level features that map more to the filters and sort of the low-frequency information in the image to map to whatever artistic style. And then people are doing now, all sorts of startups, applications, and you can run this yourself if you have GPU and 2 minutes per image. So it's not something we might want to do on every image we ever take, but it certainly is pretty impressive, the kind of results of merging and sort of the art in neural networks was something that last year was kind of a surprise to me, that so many people got interested and there were so many cool things out of this. And then more recently, specifically today as well, but last year, there's some work on using neural networks that, again, map inputs, in this case, images from video games, to outputs, which are how to move the joystick or press buttons on Atari, for example. So last year, more or less a year ago, people from DeepMind had this very simple model in describing it, which was, I'm going to give you a video game. Please maximize the score. And all I allow you to see are the pixels. And all I allow you to do is touch these 4 buttons, for example, in Atari. And then you train a neural network. And through some technique called reinforcement learning, you just try to maximize the score, let the agent train. And eventually, it actually got, in most games, superhuman. Of course, these games are in some ways cheatable because you can get 0 reaction time, whereas humans can't, and they never get tired and so on. But it was quite a cool accomplishment. I have a video that I can show, but this is online, so I'll probably skip it actually. And then today, actually, there was a new paper by DeepMind as well, where they tackled a different game, namely Go. So if you don't know, Go is sort of a chess, but fairly more complicated in sort of brute force search aspect. And again, the system was slightly more complex than the one that played the Atari game, but a key component was a neural network that took a Go 19 by 19 board, which can be seen as a black and white image, and from that board decided where it would put the next piece. So that was part of the system. There's other components, but that alone actually gets you a fairly good Go player, and the announcement was that they actually beat the best European player, and there's going to be a game against the best player in the world, perhaps in Go, in a couple of months. So if you're an enthusiast of AI and sort of hard problems that have been around for a while, I suggest you read the Nature paper, and there's a lot of press coverage about this as well. So, and again, all the components here are neural networks, which are these very powerful functions you can learn from data, which is sort of the key. So then, now I've been talking about neural networks. So what are neural networks, or at least the modern version of them? Well, a neural network has this key component, which is the neuron. And a neuron is essentially a linear combination of inputs. So basically, a neuron has a bunch of inputs. It combines them with a weighted sum. And the weights are the parameters that you will learn. And it computes the output by doing this weighted sum plus a nonlinearity. And the nonlinearity historically was a sigmoidal nonlinearity. Now people use this sort of rectified linear unit, it's been called, but it's a half-wave rectification or whatever. There's many names for this thing. And that's it. So the nice thing is that a single neuron, if you set the weights appropriately, can actually compute the three basic Boolean operations. So in a sense, if you have a network of these neurons, you have, in some ways, a general computer. Of course, how to set the weights is it's a big part of the problem. But in principle, these neural networks are quite powerful in that they can represent lots of different functions. Of course, they can actually represent any continuous functions. There's theorems for that if you have a single hidden layer. But the way I like to see it more is like representing Boolean logic that has these weights that are learned. So again, to be specific, that f of x is now a neural network that has the x and, of course, the parameters w. Those are these weights that define the weighted sums in neural networks. And it's called deep learning because, and creatively so, you just apply over and over the same principle of having neurons that take inputs and to treat these as the next step and so on. So you essentially are composing a function by, so W1 with the nonlinearity defines a function over x. You take that as the output. You define a R of W2 that takes the input as that, and so on. And as I was saying, in ImageNet, this actually goes up to like 150 layers. And in recurrent neural nets, as you'll see, it also can be quite, the composition is applied several times. So that's sort of the more specific form of this function. And then, as I said, you just train it so that it approximates the true targets. And to do so, you define some sort of loss, which is a sort of estimate of, for example, the distance between the targets and what you predict, or the cross entropy, or depends on the task, these changes. In reinforcement learning for playing games, actually the loss is something which is in like long horizon and so on. But in the end, whatever loss you defined, the advantage is that you can very efficiently compute gradients with respect to the parameters w for lots of given x and y pairs. And this is where you can kind of choose the optimization algorithm that you please. But generally speaking, stochastic gradient descent has been fairly consistently being used and successful at many of the applications that we've tried. And stochastic gradient descent essentially takes a subset of the x-y pairs that you're given in this training set, and you compute the gradient, which is now a noisy estimate of the true loss, and you update your weights a little bit, and you keep going until you converge. And so that sounds simple, but actually it's not, because the laws, and that's probably why neural nets became a little unpopular, is a very complicated non-convex function. So there's only very few kinds of neural networks that yield a cost that is convex, namely has a unique solution, wherever you start, and so on. So that's definitely a challenge to solve the optimization problem. Also, nowadays, we have lots of data, so we have many input-output examples. In text, for example, like if you take Wikipedia and you want to learn something on top of Wikipedia, you're talking about billions of words. So if each example is a word, you have lots of examples. Like this is 1e to the 9, okay? And also, W, the weights, this vector of weights, is actually quite large. So having millions of parameters to learn is definitely very common nowadays. So you can forget about things like also second-order methods, at least directly applied, because computing, for example, the Hessian matrix would require you to store a 1 million by 1 million matrix, which is quite substantial even with today's standards computers. Nonetheless, there's some efforts on solving optimization and so on, but it turns out that stochastic gradient descent works quite well in practice. And the reason of this is, as I said, firstly, you have a very small sample to compute gradients that allow you to do progress without computing a gradient over billions of examples. And secondly, the chain rule, because in the end you have this composition of many functions that are all differentiable, allows you to compute gradients actually quite fast. So the computation of gradients, if it was intractable, that would make basically training impossible. And so here is just a silly example of a one hidden layer, actually zero hidden layer neural network, where X and Y are just connected with a weight matrix plus a bias with the nonlinearity. And as you can imagine, you can do chain rule at each stage to compute derivatives. More interestingly, I think, is the fact that it turns out, I mean, at least in practice, you train these networks and you sort of train them again, and almost all the times, you don't seem to be affected by non-convexity. Namely, you start from a random position, you let the algorithm run, and you kind of get the same accuracy, the same level of precision, regardless of where you started from. So this catastrophic area where you would have a local optima that's really bad seems to not hold very much in practice, at least nowadays, with the size of networks that we have. Of course, there's noise in the system, like the gradients, and there's techniques that regularize, that add noise, further noise. But there's also some interesting theories that are coming up from Montreal, actually, that seem to suggest that, in fact, if you have a very high dimensional space, local minima is not going to be an issue anyways. And of course, we're optimizing millions of parameters. So we definitely have an optimization problem over a high dimensional space. And in practice, and some theory, especially from physics, which deals with Gaussian processes, which is not quite the surfaces we have, seem to suggest that most local minima are actually very close to the global minima. So who cares anyways? And indeed, things work. So to recap, and this is a slide I steal from Ilya, we have these powerful models that have these parameters that we somehow know how to learn via this optimization process. And the models we want models that we can learn from data and that are very expressive, and deep neural networks happen to fall into this sweet intersection of these two models. And so that's the view of why also deep learning or deep neural networks are the kind of right model to use when you deal with machine learning, especially if you have lots of data. Although there's some interesting work also on very small data sets and so on. But of course, ImageNet and these data sets generally have lots of data. However, this is not to be said, you cannot just take this as a black box. There's always some pain that's to be had. And this, the list is, I guess, in a good way for researchers like myself, quite long. So there's lots of open sort of problems or annoyances rather when you are a practitioner, but you have to sort of pick learning rates, sizes of the networks, architectures, what kind of pre-processing techniques you want to use. So there's a lot of issues that you have to deal with when in practice then you go ahead and you try to solve a problem with a neural network. So it really is not as good as it sounds. And And that's more like bridging to the next part of the talk is mostly what I've talked about is mappings from X to Y, where X and Y are sort of fixed objects, like images and whether a binary label that tells you if it's a cat or a dog. But what I'm very interested in, so especially because I have this speech recognition background, is in sequences. So how do you deal with recurrency and sequences? And first, I have a very, I'll go quickly through this, but it's important because a lot of things I'm going to say about sequences is involving words. And so words are, how do you think of words as a continuous signal? And I mean, this again has been done over and over, but it's been renamed perhaps again recently with these word embeddings, which is to say the way to input words into a neural network is as simple as representing the word as one hot encoding. So if you have a dictionary that has 100,000 different words, you literally take a word and put a 1 in the position of the vocabulary where that word occurs. And then you have this huge vector, and you can then convert it to these more like amenable vectors like that you've seen, like X and so on, via a matrix multiply, which is, of course, a sparse. So you never want to do the matrix multiply. But you have a big matrix that, let's say, is 1,000 by, so you have this vector that is very sparse. And then you have a huge matrix. This matrix is actually, I mean, we are actually preparing a submission for ICML. And this matrix right now has about 1 billion parameters by itself because we have a vocabulary of that's 800,000 words. And then we have 1,000 dimensional vector to represent every word. So do the multiplication, it's 800 million parameters. And by multiplying, and essentially the sparse multiplication is picking one of these 1,000 dimensional vectors that correspond to whichever word you want to represent. And even if you train very simple models using this sparse representation of words, such as this was recently done by Tomasz Mikolov, who was at Google right now at Facebook, you can sort of predict neighbors so you take text and you take 2 words that are close by, and you try to predict from the word sharks a word that surrounds the word shark, so in this case, ocean. And you train a model just to do that. From this word input, try to predict a word that's the neighbor of the input word. And all you do is embed these word sharks with this sparse multiplication. You train these on a large corpus, and then cool things start happening, like these vectors. Now each word is a vector of, let's say, 200 dimensions, have nearest neighbor, and the nearest neighbors happen to be somewhat related. I mean, you have all kinds of different shark, and for cars you get automobile and pickup truck and so on. And further, what they observed in the paper, by the way, this is very cool, but I don't think we found a use case for this other than being cool. But you can actually take these vectors for all these words and also do sort of basic arithmetic. So I can sort of take queen minus king, and that difference vector happens to be similar than woman minus man. So these are kind of interesting properties, and there's sort of in the paper you can see there's all sorts of things. I mean, if you take Paris minus France plus Italy, you get Rome, and so on. So there's definitely, it's kind of cool that this happened with a very simple model. It's not very deep in this case. So deep wasn't in that paper, but it still was very nice. And it sort of bridges well how to incorporate words or think of words as vectors, which then allow you to use neural networks. So the other important bit in dealing with sequences is understanding how difficult would it be to model sequences or probability distribution over sequences naively. So imagine all I want is model probability distribution over sequences of 2 words. And I have 10,000 words in my vocabulary. So to do that, I basically, if I was training what's called a bigram model, you would simply count the occurrences of every pair of words, and I would store that count, okay? What that means is I need to store 10,000 square numbers in principle if all the pairs could occur. And as you can see, as the vocabulary grows, and especially as the length of the sequence grows, this becomes quite impossible in a statistical efficient sense. So there is fortunately, another chain rule derived from base rule, which says, wait a second, don't just produce the probability distribution over pairs of words. You can do that by doing this chain rule that's exact. So you can do probability distribution of the second word given the first word times the probability of the first word. And as a result, these two probability distributions there that are factorized are over 10K. So you are doing 10K decisions, and then you do another 10K decisions instead of 10K times 10K. And in general, the chain rule reads as follows, and it applies to any sequence length. So this is great because it allows us to put proper joint probability distributions without any sort of independence assumptions over sequences. Now, these are probability distributions in general, but how do we implement these with neural networks? So to build this up very quickly and very simply, you can think of first modeling bigrams. As I said, you could just essentially take previous word, say am, and the next word would be from. And you could learn a count model or a small neural net, if you want, that maps from that word to the next word. And that would be a pretty naive model because it's assuming the words only depend on the previous words. You could do that with a large corpus of text, and that's fine. That's a very crappy language model, but it's also like fast to train, and it's actually used in several places. So you have these neural networks that map yt minus 1 to yt. But then to implement the actual chain rule is almost immediate to see that all we need is to add connectivity, not only from the input of the word t to the next t plus 1. We have to add connectivity across time in the following way. And this is clear. You can clearly see that in that case, to predict the word Barcelona, that prediction depends on not only the word from, but through connectivities of neural networks, depends also from the word am, I, and then the special token start of sentence, let's say. So in a sense, we've implemented a neural network that predicts the next word given all the previous words. And that's actually what's called a recurrent neural network. It's a fairly good language model. This was known before, let's say, the explosion of RNN research that happened maybe a couple of years ago. So this actually has been around for, the models themselves actually were in the original backpropagation paper. So, and one of the cool things that I was mentioning is if you train a 5-gram language model with smoothing techniques and so on, you get perplexities that are 74. Perplexity is just a branching factor, more or less, on every time I have to decide on a new word, how many options do I have? What's my, I'm in doubt to predict from the word I am from, I will kind of be in doubt amongst 70 words, right? And the best you can do is one word, because then you know what word comes next. And RNNs, or rather these fancy name things, LSTMs that I'll explain in a second, actually reduce the perplexity from 74 options down to 30. So they are really good at modeling language, which of course has very long time dependencies. So a hidden Markov model or a simpler model would definitely not do as well. And then you can do already things like sample these models. So despite the fact that the perplexity is quite low, and it actually is a state of the art on a this is a 1 billion word data set, so it's a lot of data. The samples you draw from this model are good, but also you could probably distinguish these are probably not human samples. I mean, the last one, for example, some of the obese people live 5 to 8 years longer than others. That seems, I mean, the world knowledge we have is probably, if there's a study that will say obese people maybe live actually not longer, but shorter. But nonetheless, it's a well-informed sentence that the model gives us if we sample this joint probability space. So we can do all sorts of things with these recurrent neural networks. And so what are these boxes that sort of connect elements? In the simplest case, it is almost as simple as the neural net I showed before. So you have sort of a state that comes from previous time steps and an input, and you have two matrices that multiply these two vectors. Remember, the x's are words, and they are embedded in this 200-dimensional space, say. And the state could be 500, 1,000 dimensional, depending on the task that you have. And so to compute the current state, there's this recurrent equation that's why it's called recurrent neural networks. That is a fairly simple neural network. And then from this state HT, you can predict then a probability distribution over words. And these W's there are learnable parameters. You feed the data set that you're given, and you get these very nice perplexities. But it so happens that there is a model, a recurrent neural net model that's much better. That's called LSTM. That stands for long short-term memory. And this was introduced, as usual, many years ago. It's not only now that people start maybe paying more attention to it. And it just has a sort of funkier recurrent equations that sort of take a state. In that case, CT and HT is the state. It's two vectors. And then it has some sort of logic that computes the next state given the previous state, and it has some sort of gating mechanism that I'll intuitively explain, hopefully, just in the next slide. And one of the cool things nowadays, if you are, I actually knew about this model in 2011, but it was sort of a pain to implement the gradients for this model because there's many parameters and you could get confused in many places. But nowadays, we have all these open source libraries. So there is almost a one-to-one mapping between the actual equations and then some Python code that will just give you the gradients for free, so you could just define any sort of model you want and then optimize given some data set. So it's very simple to define these models with frameworks like Theano or TensorFlow or whatever else is there in the open source world. So that, of course, makes many more people try these things because it's relatively straightforward to do so. And just some intuition about these LSTMs. So all I want you to note is this part here, which to the current state at time t, instead of doing that matrix multiply and sigmoid, all you do is you have this forget gate ft times ct minus 1. So that's sort of an integrator that if the forget gate, if this f was 1, or rather infinity, I guess, sigmoid of infinity is 1. So to CT, you always are adding CT minus 1. So you sort of have this leaky integrator. You always add this state to yourself. And what this allows you to do is shortcut long-term dependencies. So if I try to predict that I speak Catalan, and of course, after speak, there's going to be only a certain number of words that are possible, like languages and fast maybe and slow and so on. But if I had in my memory recorded that I've said sometime in the past, maybe 20 or 30 words ago, I said Barcelona, now suddenly the probability that I speak Catalan and not any other language should increase. But that will only be carried if you indeed can learn these long-term dependencies. And if you actually unroll the equation over time for a recurrent neural net, you will observe the thing above, which is quite difficult to optimize because you have all these nonlinearities times, and you have this WH, the matrix that is the recurrent matrix, applied over and over and over, t times steps. And what happens when if you simplify this and you think of a linear system, if you have a matrix multiplied by itself many times, it either explodes because the largest eigenvalue is greater than 1, or it goes to 0 very quickly if the largest eigenvalue is less than 1. So it poses a very difficult problem to transmit information for t times steps where t is large. Whereas these LSTMs, if you unroll the equation and assuming the forget gates do not forget, you actually get a fairly simple, straightforward connection between the outputs and inputs that are t times steps ago via through like basically one matrix multiply plus one nonlinearity. So that's kind of why the big deal on these LSTMs, that if you read a little bit of literature, you'll see there all over every one that uses RNNs uses some sort of LSTM. And then, okay, so that's sort of basic RNN. And then what we worked on mostly 2 years ago, we started this idea of mapping from sequences to sequences instead of mapping from a fixed x dimensional to y dimensional. So how to do that will become clear in the next slide. But this slide is largely updated, and note that all the dates are almost 2015. But there's been a large body of work on applying this sequence-to-sequence framework now that's been called sequence-to-sequence to all sorts of tasks where the inputs, the outputs, both or neither, well, neither wouldn't be the case, but at least one of them is a sequence. And so how would you do that, given what we know about recurrent neural nets? And that's the main idea. It's very simple superficially, but it actually surprised to us when we tried this for machine translation. It works very well. So imagine I want to map a sequence to a sequence, let's say a bunch of French words, a sentence in French to the corresponding sentence in English. So I just want to translate the sentence literally. Well, I know how to model language, in English language, very well with a recurrent neural net. That is just the right part there, where I can predict z given y, x, and beginning of sentence. So that works very well. But now, how could I also sort of model the English condition on being good English and also condition on there's a sentence I want to translate from? And then the simple solution was you add a recurrent neural network that encodes the input sequence. It doesn't produce any output. Its mission is to write to the hidden state whatever is needed for it to then spit out the correct translation into the different language. And the magic thing here is that everything, all the parameters are randomly initialized. So we literally have the simplest, almost the simplest model you could imagine for machine translation. Namely, I will need to have supervision. So I need to have pairs of sentences that are translation of each other. And after I'm given that, I put a model that literally models the probability distribution of, I want to maximize the probability distribution of the correct English sentence given the input French sentences. And I, again, will run stochastic gradient descent, pass a lot of pairs of examples, and see, hope for the best, basically. So, and as I said, intuitively, this hidden state is sort of recording. First, it's reading sort of the French sentence, putting it in memory, and then decoding that memory of the French onto the hopefully correct English translation. And then a note, a little like technical note of training versus inference. So during training, we will be given the pairs of sentences. So we know what y is and we know what x is. And then we just maximize the parameters of this neural network. But then once we've trained the model and we are happy with how it does in the training set, we need to do a different task, which is I'm going to be given the French words x, and I need to find the best possible English translation for this given by my model. So I want to maximize y. And this, of course, is a sort of challenging problem because you have many sequences, and doing it naively would be terrible. So what you end up doing is you do some beam search heuristic, which is to say you predict the first word, and you keep a bunch of candidates of good first words given by the model, and then you try all the first words as input for the second word prediction, and you keep doing that. And it's a very straightforward thing to write. I've never wrote a decoder in my life, and this was very straightforward, actually. So, and that actually works quite well. So to recap, I think in this slide is more English to French instead of French to English, but never mind that. We have a model that takes any length sequence, it passes through this recurrent neural net, and it generates this vector from which it will then decode, hopefully, onto French. And it turns out this actually is improves on most language pairs over state-of-the-art, which machine translation is a fairly old NLP task. And these, in fact, are results from Stanford, because this is Tang, who is a student here, who was an intern with us a couple of years ago and also last year. And he just won a competition where, I guess SU means Stanford University, I guess. So anyways, the numbers look good. And so all the other systems, or most of the other systems, are sort of phrase-based machine translation systems, which need the alignment between the words. I mean, they need a lot of information, and they really have a lot of tweaks. So the fact that in kind of a relatively short time span, we were able to sort of achieve very good results on translation really made the community and ourselves believe that this model that maps sequences to sequence was good. So then we tried all other things. You might have seen this too. But this is sort of a different kind of mapping where we want to caption an image. So in this case, the input is not a sequence, but the output is a sequence. And since we can do probability of English given French, to do captions very unoriginally so, we try to think of it as exactly the same way as translation is. So we will be given many pairs of images and captions, and we, again, will fit a model that can map from the image to English. And in this case, the input is a very special sequence that is of length 1. And it doesn't happen to be a word. It's actually an image. But since we have these very good models that classify objects, what we can do is take features from these neural networks that are trained to classify objects, take those features as a special word vector, if you want, on which we condition to produce things like a young girl is asleep with a teddy bear or whatever the human transcriber decided this image was like. And luckily, there was a very cool data set put together by Microsoft, actually. And there was a competition where people could submit to a server where the test data was held in place, and you could only submit 5 times, yada, yada. So the typical rules. But basically, there were, I think, 16 teams. A lot of them actually converged to use these recurrent neural networks or some form of sequence-to-sequence. Some other teams actually used other techniques. For example, one that's very different is MSR had this entry, which was nearest neighbor, which is sort of, tell me which image is closest to my training set, and that's going to be the sentence that I caption this image with. And that actually does not too bad, as you can see, in the ranking. I only put the top 8. So this was great. The results of automatic metrics of quality were superior to human, which of course should make you very suspicious. And indeed, the case was that in the competition, they asked a bunch of mechanical Turk graders for whether they, kind of the system passed the Turing test. And in that case, the 2 metrics on the right are the human metrics, which are the ones we probably should care about. And as you can see, even though there is correlation between automatic metrics and so to speak, human metrics, humans happen to be much better at being humans than all the systems that participated. So 0.6 points versus 0.2 or so points that the best systems were able to do is quite a difference. And so this problem is largely unsolved. But it was sort of going beyond this mapping to a single object, so you could map to a sentence. And then, looking at how the model performs, especially after tuning all these hyperparameters that I was mentioning, this is the painful part of neural networks. The best model after the paper submission, and which we submitted for the competition, was much better, even though the initial model graciously gave some answer that was somewhat related to the image. But in the end, the same architecture, but tuning hyperparameters and doing a little bit of sort of search over the search space that is neural networks yielded something that was, in some cases, clearly superior than the initial model. However, the initial model was way better than most of the systems that were prior to last year. I must say, as you saw, lots of groups published on this task. And now they have actually moved to sort of visual question answering or describing videos instead of still images, in which sequence-to-sequence clearly applies. But nonetheless, the results superficially at least look quite impressive in that, wow, it seems like the computer really got it. Of course, there's a lot of language modeling going on too. So if you detect there's a train, saying there is a train on the tracks is probably a very good sentence, because it's very unlikely the train is going to be flying around. And indeed, if you present the train that's flying around, it's not going to work. So the priors are very important in this model. Yes?
Compute resources required to get all the outputs the same from all the different teams?
I would say the model, so the model sizes, which relate to how much you have to use. So our model was fairly small, I would say. It was 500, the hidden state was 500 dimensions. For example, the Berkeley model had 1,000 dimensions and had 3 depths of layers. So their model was bigger, so it required more compute power, typically GPUs. So because of this data set is relatively small, overfitting is more of an issue. So actually, maybe the computational resources you use to search over parameters, but in the end, the model you end up with is fairly small and quick to run. These actually can run, you can get a caption in less than a second for any image. So you could potentially use this to to label things that you have and so on. But indeed, computational power in general for some models is important, and for ImageNet, for example, it is true that using so I think we now use 32 GPUs in parallel to train, and it takes maybe 2 or 3 days. But if a student has only 8 GPUs, well, then it will take some more days, right? But luckily, most of the data sets we use, especially when we do research, are publicly available and not that large. So it's still manageable for a grad student that has a bunch of GPUs. So another thing we tried, which was kind of more of a silly thing, but the history of this is I wondered whether we could apply machine translation, but to translate from a question to an answer. So we had this silly idea of taking movie subtitles and essentially try to predict the next conversation turn given the previous conversations, if that makes sense. And I mean, the experiment resulted on some interesting sort of, let's say, conversations, if you will, that you could have with a machine. Definitely very far from anything that would pass the Turing test, but it was very straightforward to train these models. I didn't have to make a rule-based system that dealt with conversation state and whether I said hi or no. All this was sort of given by a large set of subtitles, namely all the subtitles that were in some website, open subtitles, that something, I guess. And in general, it was sort of believable that the model would give an interesting answer. And this is again sequence to sequence. And the cool part is that somehow Google decided this was nice enough that they actually there is a product out there that does the obvious thing, which is given some short email, especially if you're on your phone, it replies to your email, and it's using sort of the same model that we did some earlier research on. So I mean, the system just essentially reads your email and decides first if it should reply automatically or not with a classifier. And if it decides that it should reply, it will put some sort of short replies, like kind of not very exciting, but that you could just click and immediately get the answer. So this is sort of a cool example from me that from the initial research paper to the applied research paper, which was the conversation paper, to then something that we launched, there was quite a quick, I would say quick, and there's a research blog post on that if you're interested, or you could try it on your phone. Please don't send emails to me. And then I'm not going to explain much of these, except the fact that there is a very challenging thing here, if you didn't realize yet, which is we need to cram all the sentences that we read, or the sequence input rather, into this fixed dimensional vector. So if we have a very long input, which we might, if we want to say, read a book and summarize the book. Now, we are trying to read word by word a whole book and hope that the state will summarize the book. So that is a very almost impossible, like, to imagine this would work. And one of the cool advances last year was the addition of memory and or attention. This has several names. And the brilliant idea is as follows. It's instead of trying to put this A, B, C, D into this box and keep putting information into it to then decode it, we will instead allow the model for, as it decodes words out, go and take a look at all the inputs it's seen. And by take a look, I mean do a memory read, sort of what you would do on a machine. So now A, B, C, D, instead of trying to put all the information through these long boxes here, they are just kind of a memory. So you have this matrix, which is number of time inputs and of size, whatever the hidden state of that recurrent neural net is. And then at the output, you say, OK, before I output X, I will go to all the inputs and see what I want to read from it, and then bring it back to the output decoder and use it to maximally predict X. And you do that, I just put that for X, but you would have this neural net being used over and over every time you produce a new output. And the math is, there's some details on like position-based attention where you attend is position-based, so it's the beginning or the end. And the thing that got introduced, which was cooler in my opinion, was content-based attention, which is I don't care where it is, but let's say I want to produce an animal because the next word seems to be an animal. Please look for animal-like things in the input, whatever they are. And then what looks like an animal, you bring it, and then you decide which animal it is. So you can do computation. So rather to have a single vector doing all the memorization of the input, you distribute the memory across these boxes, and you allow, through more computation, to read the whole memory. So that's a very cool model. I'm not going to say much more about this. And there was a related paper from both DeepMind and Facebook. The first one is called Neural Turing Machine, and the second is memory networks. But essentially, the mechanism is sort of easily described as a memory accessing mechanism. And then for machine translation, for example, without any supervision on alignments, you can see that the model is attending to the word that it's translating from and cool things like this. There was a paper on again, captioning where the word being output also many times were focusing on the output or on the region of the image that was being output. So a stop sign, it's focusing on the stop sign, and trees is focusing on everything but the giraffe and so on. And a paper that we did which kind of pushed the envelope of what would be defined to be sane to do was to try to use these mechanisms to solve algorithms. So now my supervision will be, I'm going to give you points on the plane, literally. So I'm going to give a sequence of points. And I'm going to give you also the solution of certain properties of these points. So you could imagine traveling salesman problem. So I'm going to NP-hardly solve it and give you supervision on pairs of input sequences, namely the points, and output sequences, namely the vertices. And can we train the same models to learn sort of these functions that I actually don't know how the algorithms work, or it would have a hard time for me to design an algorithm to do this in a reasonable amount of time. And so we tried this for several geometric properties. And the result is essentially is that for like very moderate number of cities, namely maybe 50 cities, the neural network was able to sort of understand the concept of minimum path given the points. And so typical errors, there's not many errors, but typical errors would be something like this, where you can see, I think here, there is some sort of error where you don't go through the quite shortest path, but it kind of got this idea that given the points, it needs to traverse them in some like optimal order. And it got that just from the data, not hard coding anything. So that was kind of cool. And just to conclude, I think there's many open problems that many people could contribute from several fields, and this is already happening given the interest on just machine learning in general, really. Deep learning is just the F part of the story. But here is a list. There's lots of open problems, unsupervised learning. Optimization has bothered me for a while, and I unfortunately haven't worked on it since I left Berkeley, but someday maybe. And it needs lots of data. So for example, to learn this concept of shortest path, we needed at least, let's say, thousands or tens of thousands of examples, pairs of points and shortest path. And I can literally show a human, even without describing input outputs, and maybe the human will get at least the concept of convex hulls are quite visual. So like data efficiency is definitely a problem, although very cool research has been going on that. And basically, I think the take-home message, the most important from my experience doing research the last 2 years is that sequences have really become first-class citizens. So now there's a very cool set of research where it's no longer scary to have a sequences of observation as the input or as the output. And we are even moving beyond that. I've myself done some work on thinking about sets instead of sequences, because some of these models, as you can imagine, for example, the TSP, the input is not a sequence of points, even though we read them one by one. It's really a set of points. And so there's all sorts of interesting aspects of learning algorithms and sort of other data structures that are interesting. And I want to emphasize that, to me, deep learning is not AI. it's really is just a mapping function that can do quite cool things, I would say. But it's sort of, I guess, if you do search like in the recent paper of today, where they combine deep learning with search to solve Go, you could mention, well, that's sort of a very hard task from an AI perspective. And deep learning certainly helped nail down or narrow down the search space that would be massive if you were to solve Go naively. And with that, I'm happy to take questions. I think we have about 15 minutes left. And this is me in Halloween. I don't usually wear dog dresses, but maybe I'll delete the original picture so it's less clear what I was doing here. Anyways, thank you very much. Thanks. So any questions?
If you want. Since you talk Turing tests, why not first do the Shannon test?
What's the Shannon test?
Well, we should have looked that up. Guessing the next character given the previous ones. That's sequence.
Okay, right.
We know we can do that with maximum likelihood match humans. I haven't seen any deep learning.
So in a sense, perplexity.
Yeah,
that. So
speech processing.
Yeah. So I was wondering that myself.
They applied that actually.
So one question that would be interesting for me to answer is what's for a given data set like the one that we trained this gigantic model on, what would be human performance, for example, if they
take 60,000 characters for a sparse sparse Markov model to match it using maximum likelihood.
Okay.
Used to run on a Cray1 teletype speed, so matching human performance.
Okay. Well,
so can you beat that with your deep learning?
I would say yes.
Anyway, that's a challenge.
Okay.
Others have redone it. Some people in Europe also didn't know some of the early work. My students did a thesis on that, but it's still cool. I guess people never read it.
Well, I will definitely read it now, so that's cool. I was actually wondering myself, I was asking some linguists at a conference last month about human performance, because I have this perplexity of, let's say, 25. Is that, are we close or not? It's not clear how humans would do in this task, because it's sort of weird to have to give probabilities, right?
Perplexity came out from IBM speech recognition.
Right.
They knew our work, so.
Right. I think speech has the nice property where
they didn't go on deep learning.
The problem in speech, I guess, is that the function you learn is deterministic to a large extent, whereas if I ask you what's the probability of a certain sentence, you don't know, right? You will know if it's a valid sentence, but
you can estimate as you go.
Yeah, so that's interesting. Shannon, I'll definitely read on that.
I would take issue with that. The problem with speech is that you have a naive audience that thinks it's going to use these things, and it doesn't see the important pathological cases with a lot of these things that only the people who work in speech know. Oh, okay, yeah, that's like the phrase, how to recognize speech and how to recognize speech as example. The naive audience doesn't see that how difficult that comparison is, and that's only within one language, the English language.
Right.
But there's actually lots of examples of that, and it gets even tougher in non-English languages.
Right. Yes.
But if it makes the same mistakes that people make.
Yeah, it does. It does make the same mistakes. People
may or may not. Ours did make the same mistakes, made different ones, but the analysis of the two, the comparison, that's the big issue, yes. That's the interesting part. How stupid or how smart errors did the machine make?
Don't forget that the first...
Stupidity can be measured on one dimension?
That's a good point that Pearson made. No, the big problem is actually a lot of the work initially was done. It was funded decades ago for only one language that most people aren't aware of. It was basically Russian and English. There was no interest in general speech recognition. Well, that only came decades later.
Yeah, that's because DARPA funded most of it.
It wasn't just DARPA, it was the rest of the NSA and the other military.
They were connected.
Indeed. Question there? Yeah.
With the traveling salesman program, is there any prospect of getting a bound on the inefficiency of the
Not
solution?
definitely not. That's a bothering point of neural networks, that generally speaking, it's hard to quantify or sort of give any assurances of correctness. And definitely in that case, it's hard to know whether you cannot prove anything, like it's 1.5 opt or 2.0 opt or anything like that. Everything is probabilistic and not. I mean, it would be quite. An advancement to actually be able to say, look, I can guarantee you with some probability you'll get an algorithm that's 1.1 optimal. But a lot of this field is, for some, of course, unfortunately, quite empirical, right? So, that's. I mean, I think in terms of specifically in neural nets and learning algorithms, which I would say is something that it kind of piqued interest maybe 6 months ago, but it has been attempted, of course, in the past. Like if you look more than a decade ago, it's mostly of the questions you typically see is, can we even do it? And then hopefully more deep questions will come as we say, well, we want to make sure we don't waste gas by doing the most stupid path you could ever do to deliver these goods or whatever.
Limit the application, doesn't it? Unless there's some.
If you care about bounds and so on, I would say yes. Yet you could definitely combine this as an heuristic for a real algorithm, right? And that's precisely what they did in Go. I mean, there's so many moves. I'm going to consider only the top 10 given by a neural network, and you might then prove that you could improve an existing algorithm by using some heuristic that is not designed by a human, but it's actually learned from data. That I think is the first real kind of impact we might see from these learning algorithms. It will not do it end to end as we attempted to just solve the problem from scratch. I think it will be a matter of integrating machine learning, which again it's also been done in some, I believe, in 3SAT and things like this, to like search algorithms or just algorithms in general. But it's a good point, and this is, I think, why some time ago neural nets were not so popular, because of lack of understanding, I guess, what they really implemented, right?
They still lack that understanding, right?
Yeah, in vision, I think there's maybe some progress there, but yeah, I mean, you analyze the optimal inputs, and this.
But what's optimal? You need some math for that.
Yeah, well, and it's non-convex.
So it's math, it's not AI.
Sure, yeah, indeed. Over there, yeah.
In your sequence-to-sequence conversion, you basically convert sequence into a state vector. And this doesn't seem to have very much temporal information there.
Right.
Was that done intentionally?
That was done sort of honestly like that. So that was a paper at NIST in 2014. What was the simplest modification we could do to our code to go from generating language to generating language conditioned on a bunch of things like French words or English words? And it turned out that if you had a large enough state space, and for the language that we tried, it indeed, that vector became big enough so that it could encode a 2 or 3 word sentence, which needs to know how to translate, and that corpus in particular has up to 70 or 80 word length sentences. But it breaks down quickly in other cases, and in that case you need attention. Yeah.
The big point is the size of that state space inside, so I assume
that's part of the pain.
Yeah.
Yeah.
Okay. So and my other question, which is kind of related to that, is if you think about the further expansion of that sort of intention and memory, that is very interesting, but that seems like it also would make the training of that whole system much more complicated and longer, because you need to now not only train the forward network, but you have to basically have that network decide what it wants to, how to name past, right? And it's not clear what's being connected in the past.
Well, yeah, so I have not, I didn't explain in much detail what that memory, and I think what is very cool about that is actually it's still a feed-forward network. So this memory, like if you actually implement the computational graph of like computing, say, a forward pass, everything is still differentiable. And so the memory, you don't do a search over what places you want to read. Everything is learned from data. So these access patterns that emerge from translation, you get these alignments that make sense. And for programs like the Neural Turing Machine paper had this sort of copying that you could see how the Turing machine was sort of writing to memory and then reading from memory. All these patterns are learned in a feed-forward fashion. So there's no like technical difference between no attention and attention.
So
It's
loop unroll?
yeah, you unroll it.
Yeah, so but that essentially says that the complexity of the networks that you're learning, the set of parameters that you're learning, then increases.
The set of parameters is constant because the attention mechanism has a matrix, a couple extra matrices that are not a function of the length of the input. But the complexity goes from ON to ON squared, roughly speaking. So in sequence to sequence, you read n words and you output n words, let's say, if it's sort of the same length. And if you have memory, you input n words, and then to output the first word, you sort of need to go and do this matrix multiply over n input symbols, and so on. So the output becomes n squared. But the number of parameters, crucially, actually, does not depend on the input length in this content-based attention. In the position-based attention, then that's why like the content-based attention is such a leap, I think, in attention mechanisms. And I mean, if
you're
you
saying that the amount of content you can have doesn't scale with the number of inputs. I mean, because it has to depend on the content.
it does. So I can show you the equations. So essentially, like you have a vector, a state vector as you decode. So here I'm trying to predict y from x, and there's this state vector of the recurrent neural net v. Okay. What attention does is it computes d transpose times the vectors that you encoded, ei. So let's imagine you encoded a sequence of length, in this case, in this example, length 4, okay? So I have E1, E2, E3, E4. I have this, let's say the input is I am a cat, okay? So I have these 4 hidden states from the recurrent neural network that encode it, okay? And then I compute d transpose times ei. So there's no parameters at all, right? So you take the output state, you multiply by the input state for each of the input states. That's the part that's ON, right? Because I need to do 4 matrix, or like rather vector multiplies. And I will get numbers that I can normalize to be from 0 to 1. And then these numbers, I'm going to use them to read this E1 through E4. So in this case, I decide I want to read position number 3 with weight 0.9. So it's sort of a soft pointer, if you will, over all the inputs. And if I have, instead of 4 inputs, if I have 8 inputs, still no parameters. You can just do the same equations. You get an 8 long vector, and you can still do the weighted sum with this vector times the E1 through E8. You get D prime, that's the readout from the input, and you're in business. So, I mean, I'm sorry if it's not super clear from this, but it really, crucially, does not depend on the length. Of course, now, if you train with length up to 100, and at test time you decide to test it on sequences of length 2,000, it very likely will fail. But there's some amount of extrapolation these models can do, actually. But so to speak, you're at the output, you have a vector. I'm going to inner product this with all the input vectors, however many they are. And I'm going to use that result to compute a weighted sum to reduce that to a single vector being a read out from the inputs. It's a cool thing that it works. And again, this is all like differentiable. So it so happens that the things we read, for example, we have a paper on parsing that it turns out that you need to build a tree at the output, and the attention mechanism was doing tracking like subtrees and so on. And we did not care what it did as long as it did, feed the training data.
You mentioned earlier that there is the set of weights associated with each neuron can be considered to compute a function.
Yeah.
Has there been any work done in relation to the total space of functions that can be usefully, feasibly calculated or computed by this model?
Yeah, so I mean, there is a universal approximation theorem that says, basically sets the ground for saying that any, like with a one hidden layer neural network, you can approximate any C1 function. I forgot. There's as long as the nonlinearity is monotonically increasing, and there's some like, and that's actually a pretty old result. And then there's some attempts again to prove that going beyond one hidden layer, it actually is helpful, because you would say, oh well, one hidden layer is all I need to approximate any function, so why would I care? So there's Joshua specifically, and then people that actually are trying to analyze random networks have some interesting results. Sanjeev Arora being one of them. So there's a bunch of work done in actually theory on why depth matters and the kind of functions they can approximate and how efficient they are at doing so. I myself don't do this, but yeah.
But there's no theoretical advantage to going to this small depth.
Oh no, there is. So that's the point. There's like, that's what I mean. In practice, it's obvious. It is useful in terms of, let's say, statistical efficiency and so on. But the paper, I haven't read it in careful enough detail, but there's a paper from James Martins very recently that actually proves there's certain functions that cannot be learned with n, but can be learned with n+1 and so on. So this, I mean, it's a sort of fascinating sub area, which, in practice, I'm not sure how much we will learn, but I hope we will learn like how to initialize things and other complicated annoyances from learning deeper and deeper models. Cool.